Welcome back to the deep dive. Today, we aren't just looking at a document. We are mentally transporting ourselves to a very specific, very intense environment.
Mm-hmm.
I want you to close your eyes for a second, unless you're driving, of course, and just imagine the noise, the dust, the organized chaos of a massive construction site. We're looking at the ABM project specifically.
And it's not just any construction site. This thing is a beast of a project.
Right. It's not just, pouring concrete. We are looking at the electromechanical side of things.
Yeah.
So picture heavy machinery moving, tight confined spaces that are hard to move in, and then you lace that whole thing with live high voltage electricity running through everything.
It is a lethal combination if you get it wrong. I mean,
Yeah.
you're dealing with the crushing hazards of heavy mechanics and the invisible instant threat of electric shock.
Wow.
In that kind of environment, safety isn't just a checkbox. It's not a poster on the wall. It's the difference between going home to your family or
Well,
not.
exactly. The stakes could not be higher. And the source material we're unpacking today is titled The Electromechanical Hazard Control Training Architecture.
Which is, I'll be honest, a mouthful of corporate speak.
And it is. It sounds so dry. But when you actually peel back the cover, this is essentially a survival blueprint. It's designed specifically for the subcontractors working on this ABM site.
It is. And the mission of this deep dive is really fascinating because I think the average person, and I'd include myself in this before I really started digging into safety science, thinks construction safety is basically just, wear a hard hat and maybe a neon vest.
The classic PPE approach. You just put on the armor and hope for the best.
Exactly. Personal protective equipment. But the core argument of this training architecture, and this is a huge shift in thinking, is that if you're relying on your hard hat to save you, the system has already failed.
Okay.
We're going to explore a much more sophisticated concept. It's called the hierarchy of hazard controls.
This is the part that really hooked me. The document lays out this hierarchy not just as a set of rules, but almost as a philosophy. The objective isn't just don't get hurt today. It talks about minimizing risks like electrical shock or mechanical failure, sure. But the ultimate goal is creating a culture of compliance.
That phrase, culture of compliance, is so key. It's moving away from the idea that safety is about a worker being careful or lucky, and moving toward the idea that the system itself is designed to prevent the accident from ever happening.
It's systems thinking.
It is. Whether you're managing a massive site like the ABM project or, just trying to manage a household, understanding how to layer these controls is actually profound.
So let's get into the meat of it. The training is split into 3 specific modules, and the document puts them in a very specific order for a reason. It's a ranking. Module 1 is what they call engineering controls.
This is the top of the pyramid, the gold standard. If you can do this, you do this first.
The definition in the text is physical modifications to the workplace or equipment. But help us understand the nuance here. Why is this considered so much better than just telling someone, hey, watch out for that saw blade?
Because human beings are terrible at being constantly vigilant. It's just a fact. We get tired, we get distracted, we get complacent.
Sure.
If a safety measure requires me to remember to do something, to remember to duck or check a gauge, it is inherently fragile. Engineering controls try to remove the human behavior from the equation entirely.
So you're designing the environment so the mistake is physically impossible to make.
Ideally, yes. The source material lists machine guarding as a primary example.
Okay.
Think about a high-speed drill or a saw with a rotating blade. You could put up a sign that says, keep hands clear. That relies on the worker reading the sign and paying attention.
And doing that every single time, thousands of times a day, without fail.
Right. But an engineer control is installing a physical metal guard over the blade. You literally cannot touch the moving part, even if you slip or you faint or just have a clumsy moment. The machine physically rejects the accident.
It stops the accident before it becomes a behavioral decision. That makes total sense.
Exactly.
Another one that stood out to me was ventilation. I feel like on a site, you see a lot of guys welding and just sort of turning their heads away from the smoke.
Which is wildly ineffective. The smoke goes everywhere. The document specifies local exhaust ventilation for things like welding fumes or handling chemicals. So you don't just tell the worker to hold their breath. You engineer a vacuum system right at the source of the weld that sucks the poison away before it even gets into the air. You modify the air itself to be safe.
Now we have to talk about isolation because for this electromechanical group, the people working with live wires, this seems to be the big one. The document references OTO.
Lockout to gout. In the electrical world, this is religion, or at least it should be.
Walk us through the scenario. Why is a LOTO considered an engineering control and not just a procedure.
Okay, so imagine you need to fix a massive electrical panel. You go to the breaker room, you turn off the main switch, and then you walk 200 feet away to work on the wires. You're stripping a wire, totally vulnerable.
You think you're
You
safe.
think you're safe. What happens if someone else, a new guy, maybe someone in a rush, walks into that breaker room, sees the switches off, and thinks, hey, why is the power out? And flips it back on.
You're fried. Game over.
Exactly. And shouting, don't touch that, isn't enough. Lockout out means you use a physical padlock to lock the breaker in the off position.
A literal lock.
A literal lock. And this is the crucial part. You keep the key in your pocket. It physically prevents the circuit from being energized. It doesn't ask the other person to be smart. It stops them from being dangerous.
It changes the reality of the switch. It's no longer a switch. It's a locked door.
And that's the aha moment the document highlights. It explicitly says these controls reduce reliance on human error. It's an admission that we are fallible, so let's build a world that forgives us for it.
They also mention automation here, using hoists and cranes.
Same logic. Don't teach a guy to lift with his knees to
yeah.
move a 500-pound motor. He's going to hurt his back eventually.
Right.
Physics always wins.
Right.
You give him a crane. You engineer the weight out of the problem.
Okay, so that's the gold standard. Engineer the hazard away. But the document acknowledges reality. This is a construction site. You can't put a guardrail on everything, and you can't automate everything. Eventually, people have to interact with the danger.
And that brings us down a level in the hierarchy. If we can't physically remove the hazard, we have to change the way people work around it. This is Module 2, Administrative Controls.
The definition here focuses on policies, procedures, and scheduling.
We are shifting from hardware to software, essentially. The hazard is still there, the wire is live, the hole is deep, but we're now creating rules to limit your exposure to it.
I found the section on work scheduling really insightful because it wasn't just about, showing up on time. It specifically calls out overhead wiring. Why single that task out?
Think about the physiology of it. You're looking up, your arms are above your head, you're balancing on a ladder or lift. It is physically exhausting.
Okay.
And when you are physically exhausted, your cognitive decision-making just drops off a cliff. You get sloppy.
So the danger isn't just the wire, it's the fatigue.
The fatigue is the catalyst for the hazard. So an administrative control isn't a physical guard. It's a policy that says no one does overhead wiring for more than 4 hours at a time, or we rotate shifts so fresh eyes are always on the job. You're managing the schedule to manage the risk.
It's a guardrail for your energy levels. I like that. The document also lumps signage and training into this category.
High voltage signs, mandatory briefings, these are necessary, absolutely. But notice they're lower on the hierarchy than the physical locks. A sign gives you information, but you can choose to ignore a sign. You can walk right past it. You can't ignore a padlock.
There's a specific call-out here for supervision, particularly for confined space entry in mechanical ducts. Confined spaces terrify me.
As they should. They are deceptively dangerous. The risk in a mechanical duct isn't just getting stuck. It's bad air, oxygen displacement, toxic fumes that settle in low spots. You can pass out before you even realize anything is wrong.
So the administrative control here is...
And I safety monitor, the spotter.
Okay.
The policy dictates you never, ever go in alone. There is always someone standing outside the hole, maintaining communication. If you stop answering, they don't run in, because then you have two victims. They initiate the rescue protocol.
Wow.
The control is the mandatory presence of that second person.
It sounds so simple, but it saves lives. The document mentions a group activity for this module, developing a checklist. Now, I feel like checklists get a bad rap as just, bureaucratic paperwork.
They do. But in safety science and aviation and medicine, a checklist is a cognitive net. It forces you to slow down. If the checklist asks, is the voltage tester calibrated? You have to mentally engage with that question to check the box. It turns an abstract policy, be safe, into a concrete set of actions.
Okay, so we've engineered the site. We've written the policies to limit exposure. But at the end of the day, someone has to pick up a wrench and actually do the work.
And that is the final layer, Module 3, Operational Controls.
I want to pause on the distinction here, because to me, administrative and operational sound very similar. The document even notes they overlap. So how do we distinguish them?
Think of it this way. Administrative controls are usually about management. The schedule, the signage, the big rules set from the office.
Got it.
Operational controls are about the worker's hands. These are the day-to-day practices and the standard operating procedures, the SOPs.
So admin is the coach drawing the play. Operational is the player executing it on the field.
That's a perfect analogy. It's the
Yeah.
habit. It's what you do when the boss isn't watching.
The source lists safe work procedures here. For example, specific steps for cable pulling or pump installations.
Right. It's not just go install the pump. It's a script. Step 1, verify power is off. Step 2, inspect the flange. Step 3, tighten bolts in a star pattern. It provides a recipe for safety so the worker doesn't have to improvise. Improvisation is where accidents happen. You want boring, predictable execution.
Housekeeping is listed here too. And honestly, from a layman's perspective, clean your room feels like a pretty low priority safety tip compared to lock out the high voltage.
You would be surprised. On a construction site, specifically around electrical panels, debris is a killer. Imagine you are holding a heavy drill, walking toward a live panel, and you trip over a coil of loose wire that someone left on the floor.
You stumble forward, right into the panel.
You stumble, you reach out instinctually to catch yourself, and your hand finds a live bus bar. Housekeeping, keeping the floor clear, is a vital operational control. It prevents the slip that leads to the shock. It's a daily discipline.
The document also highlights tool inspections.
Daily checks. Before you get in the lift, before you use the voltage tester, is the cord frayed? Is the casing cracked?
It's almost like a pilot doing a pre-flight check on an airplane.
Exactly. If you catch the defect on the ground, you don't have a failure in the air, or in this case, in the middle of a high-voltage installation. You rely on the tool to save you. You better make sure the tool is ready.
And finally, emergency response, running drills.
Because when panic sets in, your brain shuts down. You revert to your lowest level of training. If you haven't physically practiced what to do when an electrical fire starts, you will freeze. Operational controls build that muscle memory so you act without thinking.
The document has this great line about operational controls. They bridge engineering and admin gaps.
I love that phrasing. It's the acknowledgement that no machine is perfect and no policy covers every scenario. The worker's daily habits, their operational discipline, is the last thing standing between them and an accident.
So we have this really robust theory, the 3 layers. But how does the ABM project actually get this into the heads of the subcontractors? Because I'm picturing a stuffy conference room and a PowerPoint, and that usually puts people to sleep.
And if they sleep, they don't learn. The delivery method here is actually really smart. The document calls it BSL induction container-based.
Container-based, like a shipping container.
Yeah, literally inside a converted shipping container right on the site.
So you're hearing the noise, you're in the dust, you're not in some hotel ballroom with air conditioning.
Context is everything. If you teach safety in a sterilized room, it feels theoretical. If you teach it 10 feet away from the excavator, it feels real. The document also emphasizes site walkthroughs.
Taking the classroom outside.
Exactly. You walk the team to the actual electrical panel they will be working on. You show them where the Electro lock goes.
Yeah.
You point to the specific hazards. It connects the concept to the physical reality immediately.
It mentions interactive elements too, like role-playing.
Which sounds awkward, right? Let's pretend to have a safety meeting. But it forces the subcontractors to practice speaking up. One of the biggest dangers on a site is silence. Someone sees something unsafe but is afraid to say anything. Role-playing breaks that ice. It makes talking about safety a normal thing to do.
And of course, there's a test.
There has to be accountability. There's a pre-training quiz to see where they're starting and a post-training quiz. The passing score is 80%.
80%. Is that high enough?
You know, when you're dealing with lethal voltage, you'd hope for 100. But 80% ensures a solid baseline of comprehension. It means you can't just sleep through the induction and get your badge. You have to prove you understood the hierarchy.
But here's the piece of the implementation that I think is the most critical. It doesn't stop when the class ends. The document details a follow-up.
This is where most safety programs fail. They train you, give you a sticker, and then forget about you. The ABM architecture requires on-site audits scheduled within 1 week.
Within 7 days, that's fast.
Super fast. They come out to where you are working and check. Are you actually using the checklist? Is the lock actually on the breaker? Is the debris cleared up?
It proves that the training wasn't just a box-ticking exercise.
It closes the loop. It tells the worker, we are watching and this matters. It reinforces the culture immediately.
So, stepping back, we have a pretty comprehensive system here. Engineering fix the machine, administrative fix the rules, and operational fix the habit.
That's the hierarchy. And it works.
And the document notes that this isn't just something ABM made up. It aligns with, say, the Factories Act in India. It aligns with ISO 4501 internationally.
Which is important. Physics is the same everywhere. Gravity works the same in Mumbai as it does in London or New York. So the methods to prevent gravity from hurting us, this hierarchy, are a universal language of safety.
And the ultimate goal stated in the document is that culture of safety compliance.
It's shifting from reactive to proactive. Instead of cleaning up the mess after the accident, you're designing the accident out of the system before the first brick is even laid.
It's a powerful way to look at the world. And before we wrap up this deep dive, I want to leave you, the listener, with a thought. We've been geeking out on construction sites and high voltage, but this hierarchy of controls concept, it applies to everything.
It really does. It's basically a life hack for anyone.
Think about a bad habit you're trying to break. Let's say eating too much junk food. Or checking your phone constantly while you work.
Usually we rely on operational control. We rely on willpower. We say, I will just try harder not to eat the cookie. I will try harder not to look at Instagram.
Which, as we learned from the hierarchy, is the bottom of the barrel. It's the least effective method because humans get tired and willpower fades.
Right. So apply the hierarchy. Use an engineering control.
Don't buy the cookies in the first place.
Exactly.
Okay.
If they aren't in the house, you physically cannot eat them. You have engineered the hazard out of your environment. You don't have to resist because the choice isn't even there.
Or put your phone in a timed lockbox while you're working. That's an engineering control for your attention span.
Design the safety or the success into your system. Stop relying on your own willpower to save you all the time.
Whether you are wiring a skyscraper or just trying to live a healthier life, look for the engineering control. It's safer and, honestly, it's a lot less work.
Couldn't agree more.
That's it for this deep dive into the ABM project's safety architecture. Thanks for listening, and stay safe out there.
Stay safe.